Greetings. Today we'll be discussing how the motion of a star orbiting around a black hole will help us determine the gravitational force between them, and with that value we will be able to determine the black hole's mass. The purpose of this experiment is to determine the mass of a black hole using the data of a star orbiting around such black hole. We will also use the given position data of the star to determine the gravitational force that the black hole exerts. The results found in this experiment show that knowing the motion of a star orbiting around a black hole is fundamental in order to determine the gravitational force that is acting between them. This result was observed by writing the initial data in the code. By this, we are doing the reverse process of the calculation of the predicted motion of the star around the black hole. The overview of the experiment system is the star orbiting around the black hole. The fundamental physics principles involved are the momentum principle, which is delta p over delta t equals Fnet, and Newton's law of universal gravitation. The surroundings is the black hole. It is important to remember that we are using the momentum principle in order to calculate the total force existing in the interaction between the star and the black hole. We will see this equation in a more developed way in the Python code. Now here's the data. The star mass was 1.9890 times 10 to the 30 kilograms, and those are the initial time, the black hole's position, the star's initial position, and other important information. The procedure used to calculate the results was this important equation, which is dp/dt perpendicular plus dp/dt parallel equals dp/dt, which equals Fnet. The important thing to notice from this equation is that dp/dt perpendicular is equal to Fnet perpendicular, and vice versa with the dp/dt parallel and Fnet parallel. This was the magnitude of the final position of the star in order to calculate the arrow scale, which is this process, because the arrow scale relates the star's motion and the force. Now we can see the Python code. In the origin, I chose the radius of the black hole to be 5 times 10 to the 10 in order for us to see it when the code is running. A black dot will appear representing the black hole. This is the initial conditions, and here we can see that I indicated the Vital to search this CSV file for it to collect the X and Y positions and store them in a list. And this list will later prove very important to calculate the velocity, and later velocity will be used to calculate the final and initial momentum. Here is the process of calculating Fnet, which equals dp/dt. And here, to calculate dp/dt perpendicular, we didn't use the equation of mass times velocity squared over radius, because we don't have the radius of the kissing circle. Now here is the value of the arrow scale, and here is the process of calculating the black hole, the mass of the black hole, which is magnitude of force net times magnitude of the radius squared over g times the mass of the star. When we run the code, we can see that these values will be printed. This one is the black hole's mass. As you can see, the arrows, the blue arrow, the yellow arrow moves towards the position of the black hole. The blue arrow represents Fnet perpendicular, this represents Fnet, and the black arrow represents Fnet parallel. Now we're going to answer the what if question. Is it possible to find a value for the mass of the new black hole. It is not possible to find a new different value of the black hole because it would undoubtedly change the orbiting motion of the star. If the motion of the observed star remains the same, it will mean that the mass of the black hole remains unchanged. What does it mean? The answer to this question is, in essence, that both values are equal magnitudes, but they represent different purposes. For instance, TPDT describes the motion of the star, and FNet basically represents how it affects the star's motion. Thank you for your attention.